Hello, and welcome to Math with Mr. Bill. I'm Bill Anderson, and today we're going to be discussing ways to find an integral without actually taking the integral. The setup is a little unorthodox, but I think it makes for an interesting problem. If you have any questions, please feel free to put them in the comments below, and if you have any other problems, feel free to put them down there as well. So let's read out this problem. It asks us to evaluate the following integral, showing the steps as indicated. We're going to find the integral from 1 to 5 of the square root of 3t plus 1 dt. First thing we're asked to do is to set up an integral function in the form of a of x equals the integral from a to x of f of t dt. So let's go ahead and do that. It'll just be a simple replacement. So if you look in the integral, our f of t is given by the square root of 3t plus 1. So looking at a of x now, we can make that equation the integral from a, the little a, which is the left end of our interval, which is going to be 1, to x of f of t, which is the square root of 3t plus 1 dt. Okay, so now it asks us to sketch a graph which displays the area that this function represents, labeling the key points on the graph with their coordinates. So let's set up a coordinate plane. So the key points here for this is what happens at the end of the interval. So we want to know what is f of 1, and we want to know what f of 5 is. So f of 1 is the square root of 3 times 1 plus 1, which is the square root of 4, which is 2. And then f of 5 is the square root of 3 times 5 plus 1, which is the square root of 16, which is 4. So let's put those points in. So those are the points 1, 2, and 5, 4. And then we're going to draw a nice gentle curve between the two. And so the area underneath this curve is what that integral represents. So now it asks us to state two facts you know about a. The first being an input, which makes calculating the integral trivial, and the second is to state the derivative of a of x. So we have a of x equals the integral from 1 to x of the square root of 3t plus 1 dt. And the input that makes this trivial is the number that would make the top and bottom limits of this integral the same. So it's a of 1. So a of 1 is equal to 0. And then it asks us to find the derivative. Well, using one of the parts of the fundamental theorem of calculus, we know that a prime of x is just equal to the inside of the integral with the t replaced with x. So then, what does it ask us? It says to use your two statements to construct a formula for a of x which doesn't use an integral. And this is an interesting way of looking at the integral. So what do we know about what we're, what sort of fact can we use here? Well, one thing that we can use is the idea that we can find the antiderivative of a function. And so looking at a prime of x, we could, if we wanted to, we could find the antiderivative of that without resorting back to the integral form. So the antiderivative of a prime of x equals a of x plus a constant. But a of x is not our integral this time around. We're going to go backwards using antidifferentiation. So let's take a look at what that means. So if a prime of x is equal to the square root of 3x plus 1, I'm going to make that 3x plus 1 to the 1/2. And we find the antiderivative of it. So a of x here is equal to, well, what would we do? Well, to find 3x plus 1 to the 1/2 as a derivative, we would take the exponent of our original function and subtract 1. So what would we subtract 1 from to get 1/2? Would we get 3/2? That 3/2 would come down front. And if you look at the derivative, we don't have a 3/2 out there. So there must have been a 2/3 in front of our original function in order to get rid of that 3/2. That would be the outside part. And then we've got this inside part we've got to deal with. And if we take the derivative of the inside, we would get a 3 to come out to the outside. Well, we don't have a 3 out there either, so we've got we don't have a 3 out in the original one, so we have to multiply this whole thing by 1/3 in order to take care of the 3 that's going to come out as the derivative of 3x plus 1. And then we add in our constant because we don't necessarily know if there's a number being added to the thing we're taking the derivative of, because the derivative of a constant is 0. So if you're looking at the derivative and you want to go back to the original function, there's no way to say, oh yeah, there was, there's a 5 there. There's just no way to say that. So we added this constant to see if we can figure out what that is later. And if you need convincing that this new a of x is actually the function that we're going to be dealing with, take the derivative of it and see if you get a prime of x. And you'll see you will. Okay, so there's our new form for a of x. We've got to figure out what this c is, and that's what the a of 1 is good for. So a of 1 is equal to, it's going to be equal to the function here with 1 put in. So 3 times 1 plus 1 raised to the 3/2 plus c. And we also know that it's equal to 0, because that's what we said before, is that a of 1 is equal to 0. So now we can evaluate this, and we can actually solve it for c. So we have 2/9 times 4 to the 3/2 plus c. 4 to the 3/2, well, we've got the square root of 4, which is 2, and then 2 cubed, which is 8. So we've got 2/9 times 8 over 9, or 2/9 times 8 plus c. 2/9 times 8 is 16/9 plus c, and we know that that's equal to 0. And so c is equal to negative 16/9. Okay, so now we've got an entire picture for a of x. So a of x is equal to 2/9 times 3x plus 1 to the 3/2 plus c, which is negative 16/9, or minus 16/9. And then the last step for this problem is to determine what the area is. So we find a of 5, because that's the upper limit to our integral. And that's going to be equal to 2/9 times 3 times 5 plus 1 to the 3/2 minus 16/9. So 3 times 5 plus 1 is 16. And let's move that over here. So we have a of 5 is equal to 2/9 times 16 to the 3/2 minus 16/9. So that's equal to, so 16, square root of 16 is 4. 4 cubed is 64. 64 times 2 is 128. So 128 over 9 minus 16/9. And we put those two together and we get 1/12 over 9. And that's the area of that amount under that of the curve. That's the area underneath that curve, 1/12 units squared. So that's it. We finished that problem. If you have any questions, let me know. Otherwise, we'll see you for the next problem.